Hello, everybody. Um, we're going to have a brief discussion about rolling about slipping, K, rotational, and kinetic energy in general. So let's do the kinetic energy part. One of the things that we've learned is that the kinetic energy is 1/2 the total mass and the velocity of the center of mass squared. And it's important to recognize this as the center of mass velocity. And I'm now going to call this K translational. And this just represents, again, any old object you want moving. And it's moving in a straight line, which is called translational. We saw briefly in the other lecture that we can have a rotational kinetic energy based upon how something rolls. So in this case, what's happening is we have an object. It has a moment of inertia, I, usually a radius, usually in a, so that we can figure out what I is equal to. And it's rotating. So the ball is coming down and doing that for its rotational direction. And when balls roll that way, that's the direction they go. I check with my pencil, which you can see. You roll into it. So let's examine two things. First is, let's zoom in on the landing zone, if you will. And when we blow that up, we see the curve of the wheel and the floor. And the curve of the wheel has a force of friction this way. Which means the floor has that force of friction which is going in the direction of the motion. So it's the floor pushing on the wheel which makes this possible. And you've experienced this if you've ever spun out. You spin your wheels like crazy and they don't go anywhere. And that is a condition we call slipping. So, oops. Slipping is when the velocity of the center of mass is all you have. Because this is the no friction case, so the velocity is just going to slide right across that slipping case. Most importantly, without slipping, we don't get a rotational motion. So the second thing I want to talk about then is going to be this idea of we can combine and have a new definition of kinetic energy, which is given by 1/2 mv center of mass squared plus 1/2 I omega squared. Translational, rotational. And we can do this because we know what the center of mass is. Meaning that if I set up a coordinate system, and let's put a wheel, oops, just missed, well, rolling on it, so let's make it a solid disk. Then the center of mass would be right in the center, and any vectors we would be drawing would locate the center of mass at that location. As the wheel moves down the track, what we're going to be doing is changing the location of the center of mass. So as the center of mass moves, so let's get that other vector back there. Okay. Then as the center of mass moves over time, we know from these position vectors, so we'll just call them R and R and R, that these vectors, R1, R2, track the center of mass. And if this happens over time, then we get the velocity vector forming between the center of mass motions. Okay, that should go all the way in. However, the wheel can be rotating. So, as the wheel turns, about that center of mass, what we're saying is, let's draw the vectors to each and every chunk of mass in this disk. So we're going to have just an infinite quantity of these molecules that we need to add up in a way that tells us how they are distributed. And that is how we wound up with the kinetic energy of rotation equaling 1/2 I omega squared. Because the I takes into account all of the locations in the masses, as well as the mass themselves. So it's a twofer. It's the mass total, and it's the location of every single molecule in the map. And the rotation is going to do its own thing. So as we showed with the center of mass motion, it travels right along, and that gives us the kinetic energy total. And since we've always historically reduced the mass to where the center of mass acts, that's kind of the point of center of mass, we get our definition of the translational kinetic energy. And because the thing is rotating, we have to have a rotational term. So there can be a bridge between the two. So let's take our wheel again. That's an ugly wheel. Let's take a wheel again and think about what's happening. The center of mass motion is going off this way with V center of mass. And we know the wheel is rotating about the center of mass. So I'm getting a omega this way. If we, again, zoom into the bottom of this interaction with the floor, and the sphere, son of a bitch. There we go. So if we have no slipping, that means we're running on static friction, because at the point of contact, the wheel is going this way due to omega. So this is V tangent. And it is exactly equal to the V center of mass. That's what no slipping looks like. Find something round in and around your desk and look for, and just play with it and watch what happens when the round object makes contact with the ground, that from the point of view of the round object system, it's producing a tangential velocity. But from the point of view of the lab, which is where we're at, as it moves, that point stays stationary when it hits the ground. So that contact point stays stationary if it's not slipping. So that means I can write the velocity tangent is equal to the velocity center of mass. And therefore, the velocity of the center of mass is given by the radius of the wheel times omega. So this is our rolling without slipping conditions. And if we achieve this, things become a little bit easier. So, for example, let's build a hillside. D And we'll make this a ring going down the hill. We're going to have our two velocities. We're going to have the velocity of the center of mass as it goes down the hill. And we're going to have the fact that it is now rolling, giving us a second velocity. So let's write out the total kinetic energy. First, I is going to depend upon the radius and mass of the object. So let's give this a simple radius of 10 centimeters. And it started at a height h of 3 meters. And we need a mass, which we'll just make 250 grams. So we start with the eye of the ring because that's going to be the 250 kilograms. That's the mass. And from the table, we know this is just the radius, 0.1 squared. So I is going to be nothing more than 0.25 times 0.1 times 0.1, because it has to be 0.1 squared. And we get 2.5 10 to the third kilograms meters squared. That's what I has as its units. Okay. So now we go into our total kinetic energy of the wheel. And if I may be so bold, we know that's just going to equal, from energy considerations, the gravitational potential energy. Initial and final. So this is all coming from delta E of the ring system equaling 0. Okay, so K total, get the back to black. K total is our 1/2 mv squared plus the 1/2 I omega squared. The linear piece is very familiar. So that's 0.25, and we don't know the velocity. That's what we're looking for. Plus 1/2 I, which we found up there, and omega squared. But let's take our omega squared and grab it from this equation. So omega squared is going to equal the velocity of the center of mass divided by the radius that's rolling on squared, and let's put this all together. So I'm going to get 0.5 times 0.25 would be 1.25, yeah. So I get a 0.125 v squared plus the 1/2 2.5 10 to the cubed don't know the v center of mass yet. That's kind of what we're looking for. And we do know that r in this case is 0.1, and we're going to square all of this. So pull our unknown out, v center of mass squared, and I get 0.125, and that's in kilograms. Then we're going to add it to the 2 point, sorry, I really did mean add, and that's not what I wrote. We're going to add to this all the numbers. So 0.5 times 2.5 e to the, pretty sure that's the negative third. And now I'm going to divide it by 0.1. And we get 1.25 10 to the 4. It is 10 to the 4th. Oh, did I put that in wrong? I'm going to have to clear all this because that's also 0.1 squared. So I'm going to get 0.5 times, clear, 0.5 times 2.5 e to the negative 3 divided by 0.1 divided by 0.1. Alrighty. So this gets us a value of 1.25 to the minus 1 v center of mass squared. Oops, I'm sorry. I forgot we had factored that out. So let me get rid of all that and just close this off, noticing that if I take the moment of inertia as units, kilograms over meter second, and divide it by the radius, which is in meters seconds, I again wind up with units of kilograms in here. So we add the insides. V center of mass squared. Everything over here is 0.25 just kilograms. I'm going to bring in the mass, 0.25 kilograms, 9.8 for G, and the height of 3 meters. So this is just remembering that UG is equal to mgh. Oddly enough, and this will not happen very often, I'm going to be able to cancel out my masses. That's just unheard of, actually. And then the velocity is going to come in to be units of so 9.8 meters per second times meters gets me meters per second meters squared over second squared over here, and I'm going to then take the square root of both sides and get 9.8 times 3, and take the square root of that. And I get a velocity of 5.42 meters per second. For comparison, no rotation, or maybe even just slipping, I would get my U of gravity initial would equal my K total final, but K total in this case is just going to be 1/2 mv squared, because there's no rotation term. Mgh for the initial, the masses cancel out, and I get v is equal to the square root of 9.8 meters second squared times a height of 3 meters, and 2 times 9.8 times 3 . This velocity is 7.67 meters per second. Notice that in comparing the two, we're going slower when we're rolling, because the initial gravitational potential energy is used to rotate the object, in this case our disk. So essentially the gravitational potential energy has to be split when we're up in this situation. It needs to be split here. Our K rotation has 2 terms, and the gravitational potential energy has to climb into and account for both of those terms. Without rotation, our kinetic energy I can't believe that just happened. Anyways, our kinetic energy is split between our mgh and our 1/2 mv squared. Okay, hope that helps you understand a little bit about rolling without slipping and where the kinetic energy rotation comes from.